So now let's cover the most recent thing that we've talked about, which is, what happens in real fluids where you actually have interactions. The first question is, a 1-inch, 2.5 centimeter diameter garden hose will carry far more water than a 1/2-inch diameter garden hose, everything else being equal. This phenomenon is explained by the fact that the wider hose, one, has less inside surface area and therefore exerts less static friction on the passing water. 2, has a higher Reynolds number and therefore induces less turbulence into the flowing stream so that it can travel faster. 3, has less inside surface area and therefore exerts less sliding friction force on the passing water. 4, has more room for the water to pass through and places much of that passing water farther from the walls of the hose so that it can travel faster. Remember that the thing that I've emphasized in the past has been the Bernoulli equation, and remember that this sort of relates essentially conservation energy for fluids. So you have a kinetic energy term, which I just wrote, and then you have a potential energy term, and you've got the pressure potential energy term, and the idea is that this is a constant. Now, what I've said a number of times is that this really is not really correct, because it assumes essentially that there are no losses as the water goes through it. And what you know is that you always have interactions. And so the idea is that as water flows through a pipe, then essentially it's fixed to the walls. It's moving very slowly past the walls, and the velocity in the center is the fastest. And that's because of the interactions of the fluids among itself, and also with the walls. And so the reason why you get more flow through a pipe when it gets bigger is that essentially it's farther from the walls, and so more of the center of the pipe is free to move without actually having too many energy losses. And so this is why the fourth one is the appropriate answer. It doesn't have anything to do about surface area, and it really doesn't have anything to do about turbulence or Reynolds numbers. It's just merely that being far away from the walls means that there are less interactions, and so more of the water is able to go faster. And it's a huge effect. In other words, the flow rate, the amount of volume that you get per unit time, depends on the pressure across the pipe. But it also depends as the radius to the fourth power of the pipe. So if you double the size of the pipe, you can get 16 times the amount of flow rate. And then down here basically is the viscosity, approximately. There's some other constants in there. Next one is that when a hurricane wind blows horizontally past the peak or domed roof of a house, they tend to lift the roof upward and pull it off the house. This upward force develops because the airflow bends downward towards the roof as it flows over the top of the roof. This downward bend towards the roof's upper surface indicates that the air pressure at the roof's upper surface is 1, equal to the normal atmospheric pressure, and that there is a strong, unbalanced viscous drag force on the roof that's pushing the roof upwards. 2, lower than the normal atmospheric pressure, and there is an unbalanced pressure force on the roof that is pushing the roof upwards. Higher than normal atmospheric pressure, and that there is an unbalanced pressure force on the roof that's pushing the roof upwards. 4, equal to normal atmospheric pressure, and there's a strong, unbalanced pressure drag force on the roof that is pushing the roof upwards. And again, the idea with this is if you have a house with the roof on it, and imagine that you have a really strong wind. The idea is as it goes over the roof of the house, it has to basically follow the roof of the house. And so the idea is that these, lines of flow essentially are moving in a circle, which means that there has to be a centripetal acceleration, as always. And how do you apply a centripetal acceleration? Well, you essentially have to have an unbalanced pressure. So if it's atmospheric pressure when you're away from the peak of the roof, as you get close to it, in order to get a net force on it, you have to have something which is at a lower pressure, basically next to the roof. So the atmospheric pressure far away, and as you get closer to the roof, the pressure goes down. And since the pressure inside the house is presumably at atmospheric, what you end up getting is an unbalanced pressure on the roof, and it tends to lift the roof off the house. And it's just a lift force, basically, on the roof. So it's lower than normal atmospheric pressure, and there's an unbalanced pressure force on the roof that's pushing it upwards, mainly between the inside and the outside. So it's this one. Okay, third one. This one's similar. You live in a cylindrical high-rise apartment building. It looks like a giant upright can with windows. Your apartment has a window on the south side of the building, and you have noticed that the air pressure outside that window varies according to the direction of the wind. That pressure affects airflow in or out of your window. When the wind blows from the west to east, the air pressure outside your room window. And the idea is that you have a building that looks like this. You're sitting basically on the south side, and you have airflow going from west to east. And so the airflow has to go around, in particular. Therefore, the flow is essentially circular, which means that there has to be a centripetal acceleration. So if it's atmospheric pressure out here, then again, the pressure has to be lower next to your window. So if you have atmospheric pressure inside, then when you open your window, you'll tend to get flow outside your window. So the idea is that just outside your window, the pressure is below atmospheric pressure. And because it flows out of your window, because the pressure inside the building is atmospheric. And so it's definitely this. It's not above atmospheric, so you can get rid of these. But air flows out of your window, not into your window. Okay, fourth one. You can add a thickening agent to soup to make the soup much more viscous without changing its density. You are stirring 2 pots of soup, one without the thickener and one with the thickener, using identical spoons. You find that the thickened soup becomes turbulent at a lower stirring speed than the unthickened soup. 2. The 2 pots of soup become turbulent at approximately the same stirring speed. 3. Stirring speed has no effect because both pots of soup remain laminar at all speeds. 4. The unthickened soup becomes turbulent at a lower stirring speed than the thickened soup. And again, this has everything to do with the Reynolds number. Basically, the idea is that you have something that involves inertia as a mass, which really means it's the density of the fluid, depends on the velocity in the numerator. And then down here you have the viscosity. The larger the Reynolds number, basically, the easier it is to get turbulent flow. And so if you have a low viscosity, then you'll get turbulence at a lower speed. So the idea is the unthickened soup, because it's not the viscosity is quite small, it becomes turbulent as a lower stirring speed. And so this is what's going on. All you have to remember is the Reynolds number depends proportional to the velocity and inversely proportional to the viscosity. So that's pretty much everything that you need to know about these real fluids.